combining Eliashberg theory with density functional theory for the accurate prediction of superconducting transition temperatures and gap functions. A. Sauna Max Planck Institute für Mikrostrukturphysik, Weinberg 2, D06120 Halle, Germany. C. Pellegrini and E. K. U. Gross Fritz Haber Center for Molecular Dynamics, Institute of Chemistry, The Hebrew University of Jerusalem, Jerusalem 91904, Israel. Received 3 January 2020, revised 10 May 2020, accepted 18 June 2020, published 27 July 2020. We propose a practical alternative to Eliashberg equations for the ab initio calculation of superconducting transition temperatures and gap functions. Within the recent density functional theory for superconductors, we develop an exchange correlation functional that retains the accuracy of Migdal's approximation to the many-body electron phonon self-energy, while having a simple analytic form. Our functional is based on a parametrization of the Eliashberg self-energy for a superconductor with a single Einstein frequency, and enables density functional calculations of experimental excitation gaps. By merging electronic structure methods and Eliashberg theory, the present approach sets a new standard in quality and computational feasibility for the prediction of superconducting properties. DOI 10.1103 FIS Revlet .1251 0.1103 FIS Revlet .125.057001 10.1103 FIS Revlet. One of the great challenges of modern condensed matter theory is the prediction of material-specific properties of superconductors, such as the critical temperature Tc and the gap at zero temperature. The model of Bardeen, Cooper, and Schrieffer, BCS, accounts for the universal behavior of all conventional superconductors, but is not able to describe material-dependent properties. 1. A major step toward a first principles approach to superconductivity is Eliashberg theory. 2. Within the latter, all the relevant quantities that govern the superconducting properties of a material are calculated in the Nambu-Green's function formalism. 3. 4. Using the analog of GW as approximation for the self-energy, where W refers to the screened Coulomb interaction, plus a renormalized phonon propagator. By virtue of Migdal's theorem 2, 4, 5, which states that the neglected terms in the perturbation expansion of the self-energy are of the order of the square root of the electron to ion mass ratio, this method describes electron-phonon coupling effects very accurately. However, the treatment of Coulomb correlations is much harder, and in practice, the electron-electron repulsion is usually modeled by an adjustable parameter μ, chosen as to reproduce the experimental Tc 6-7. In its common applications, thus, Eliashberg theory cannot be considered a truly ab initio theory either. Combining good accuracy with moderate numerical effort, density functional theory (DFT) is the method of choice for ab initio calculations of material-specific properties in the normal state. Following the discovery of high-temperature superconductors, the formal framework of DFT has been generalized to describe the superconducting phase of matter. 8. Compared to traditional many-body approaches, DFT for superconductors, SCDFT, yields two major advantages: the computational feasibility of the equations and the absence of any empirical parameter, such as the μ of Eliashberg theory. In SCDFT, both the normal density nr and the superconducting order parameter R0 hash of the system are reproduced by a non-interacting Kohn-Sham Ks system, where the exchange correlation XC effects on superconductivity are included via the pairing potential SR R0 hash 1/2 n chi. Within the so-called decoupling approximation 9-11, the diagonal matrix elements of S with respect to the normal state Ks block orbitals SK 1/4 h key play the role of a BCS gap function in the quasiparticle excitation spectrum. Ek 1/4 for phi 2k hash JSK J2q, where k are the eigenvalues of the Normal state Ks orbitals with index k 1/4 k, n, i.e., block vector k, and band index n. The Ks system is fully determined by solving the BCS-like gap equation. Sk 1/4 zksk 1 2x. K0 kk, K0 tan beta 2 x0. X0 sk0, 1. Published by the American Physical Society, under the terms of the Creative Commons Attribution 4.0 International Creative Commons Attribution 4 license. Further distribution of this work must maintain attribution to the authors and the published article's title, journal citation, and DOI. Open access publication funded by the Max Planck Society. Physical Review Letters 125-057-001-2020. Editor's suggestion featured in Physics 0031-9007 equals 20 equals 1255 equals 057001 6057001-1 published by the American Physical Society. Where beta is the inverse temperature. The kernel of this equation consists of two parts, a diagonal part zk, which acts as the renormalization term in the Eliashberg equa.